Okay, so let's see. So various announcements. So first of all, I'll be placing all the lectures and the problem sets on. Just 1 second. Let me do one piece of bookkeeping here. Oh, something funny is going on. Okay, well. That's what I should be doing. Sorry, some technical difficulties. All right, okay, I'm back. Okay, so yes, so Canvas will be an important, and Slack will be important sources of information. There's a lot of options on Canvas, but everything will be under files and under pages. So files will have the lecture notes, problem set, solutions, various readings, section lecture notes from how you, and so on. And I'm going to be using my iPad for the lectures, and the recording of the PDF of my writings will also be on Canvas. It's all under files and pages. Some things under pages. Okay. Now, in terms of grading and so on, I guess there were going to be 5 or 6 problem sets through the entire semester, and then a course presentation. Now, initially, I thought this would be an in-class presentation, but if you really have 39 students, that's not going to work. So I would probably ask that you make a PowerPoint or a keynote presentation, and then we can meet at various times. And of course, others can also attend. The purpose of the presentation should be to explain some recent topic of research to your fellow students. So if you look under the pages section on Canvas, there's a page there on Crow's presentations. So here 2 students have already decided what they're going to talk about. So I've listed the topics, and there's no rush on this. Maybe by the end of October, early November, if you have an idea of what you want to do, you can discuss it with me, and I'll also maybe post suggestions for topics in this page. And then once you've decided what you have, I'll post it on this page. Okay. All right. So maybe I'll turn it over to Hayu if you have comments about section then. So the sections will be an integral part of the course, and often Hayu will cover some needed background that some of you may not have. For instance, this week I'm going to talk about path integrals, which we're going to start using in lectures next week.
Yeah, so the sections will be on Thursdays from 4 to 5 p.m. So it's basically I will cover some materials like that has some background information that may be used in the main course, and also I will try to cover some homework problems when pieces are out. Yeah.
Yeah, and both of us will be on Slack for questions and so on, and we can have office hours. Well, let's see how it all develops. Okay. Does anybody want to speak of, have other questions before I'll discuss the course outline, and then we'll just start.
Do we have lectures Monday, Wednesday, and Friday, all 3 days?
Yes, that's my initial plan, but I'm going to make them, stop at 4. I thought it'd be better to have shorter lectures, but on all 3 days. Yes, but they'll be recorded, and if you can't make all 3, well, that's fine. You can always watch the recording. There's a fair amount of material I want to get through. And if I, as we'll just discuss all the things that we want to talk about, it's hopefully we get through it all. We'll see. But that's the plan, yes. But I won't go over an hour. So this will be the way the courses used to be, 1 hour each on Monday, Wednesday, Friday, or a little less than an hour each. Okay. All right, so let me just go share the screen and just go over the syllabus. Okay. All right. Yeah, so here's the list of topics. I think you can all see that, can't you? Yeah. So I'm going to begin, this is parts 1, 2, 3 are really topics that are covered in depth in Physics 295B, which is the traditional course in many body theory. But you really don't need to have taken that. This is why I'm covering just the basic ideas, what we're going to need. That course, goes into details on Feynman diagrams, Green's functions, and we won't use them very much. And if I do, I'll define what I'm doing. But anyway, we do need to cover, what are called the familiar phases of matter, which are metals, solids, superfluids, basically, and superconductors. And I'll discuss, their basic properties and review them. And then starting from roughly topic 5 onwards are really a set of modern topics. These are kind of new phases of matter that have really come to the fore in the last 20, 30 years, involving new types of phenomenon. I guess the word entanglement is used often. I'll try to make it more precise. This started with the fractional quantum Hall effect, but now there are various spin liquids in different systems. There's, connections to various connections to quantum information theory to some extent, and theory of topological order, which we'll touch on as we go on. And so there's a lot to do there, and I've tried to organize it in a way that I think is the best way to understand things in the simplest possible context. So we'll see how that goes. And then towards the end, we'll go back to topic 1, which is metals. These are conducting compounds which have things called Fermi surfaces, and also various exotic states that they can form, which may be relevant to lots of experiments on metallic, strongly coded metals, which is a topic of much study these days. So that's kind of the ambitious outline. There's, a lot more to be done on these topics, and a lot of current research that I myself am not familiar with. So I'm hoping some of you will use these as starting points for other topics in current research, and educate your classmates and also me on something else. Okay. All right. Any other questions? All right. So now where's my Zoom thing gone? Oh, stop share. There it is. All right. So another thing you'll notice, assuming this works well, that there's 2 of me. The other of me is on my iPad, and now I'm going to switch to the iPad and start the lecture on the iPad after sharing the screen. So let's see. Come on, what's going on? I hope this doesn't crash now. Oh, okay, there we are. So it was tricky the first time around, and there. Okay, so you should all see my iPad. All right, lecture 1, Fermi liquid theory. So what I'm going to try to do, as you can kind of see here, there are prepared lecture notes that I have here, which are already on the website. And I'm going to go over them, but also add more remarks which are on these blank pages that I'll insert every now and then. Okay, all right. Okay, so here's the general class of problems we might be interested in. You have a bunch of particles, typically n particles. I goes from, wait a minute, okay. I goes from 1 through n. And these have some kinetic energy, which is here. And let me see, change the color of that. And some lattice potential, so these could be electrons moving in some lattice. So this is some periodic potential for most of the course. And then some interactions between them. And we want to understand, the set of possible phases of a Hamiltonian of this type. And there's no way there's a complete classification. The set is really huge. But people are learning now to at least divide them into different classes, and we want to study the most well-known classes in this course. Mostly, I'm going to assume that the particles are fermions, although topic 2 will be bosons, but for now, for this lecture anyway, let's assume they are fermions. Okay, so given a problem like this, what do you do? Say you want to find the ground state wave function. Now, this is an impossible equation to solve with this with n particles and interactions between them. So what's typically behind what's in the standard textbooks of condensed matter theory is you would call the Hartree-Fock or mean field approximation. So the idea is that you pick some set of single particle orbitals. Let me call them phi A of R. And if you have n particles, well, A will say run from 1 through n. And then the wave functions of the n particles, psi of Ri, you will say is what's called a slated determinant. It's the determinant of phi A of Rj. So just an example to make it clear for the n equals 2, this would be something like the following statement. You have two orbitals, let me call them phi A and phi B. So phi A of R1, phi A of R2 in one column, and then phi B is some other orbital of R1, of R1 and phi B of R2. So say the orbital index runs over, in this case, the columns, and the row and the particle index runs over the rows. And now, why do we write it this way? Well, what we're saying really is that these particles occupy these orbitals, single particle orbitals, and the full wave function is just a product. But that's not good enough because the wave function has to be anti-symmetric globally. These are fermions. And so you anti-symmetrize the product wave function by making it into a determinant. Now, for bosons, you would do the same thing, except you'd miss the minus sign, and that's called a permanent. So for bosons, you just replace the determinant will become what's called a permanent. That's just like a determinant without the minus signs. All right, and then the task is you pick some orbitals, and then the statement is that you minimize. It's the variational principle. You minimize psi, h psi. Over what do you have variational parameters? Well, the variational parameters are these functions, phi A of R. So you have n functions, but this is a much simpler problem than the original problem because each function is a function of only one coordinate. If we did the variational problem on the original wave function, you'd have one function, but of n variable. That's a much more complicated beast than a function of just one variable. So you have n functions of one variable, and you just have to minimize and determine the best possible phi A. And this can be done, very systematically, numerically. There's extensions of this called density functional theory that can really do this and also include some corrections from parts of the wave functions that are not simple products or determinants. And then you can talk about excited states and so on and so forth. And really, that's a very quick summary of solid state physics until the 1980s, I would say. Almost everything in solid state physics is a small variation of this kind of variational calculation. And it's, for good reason, it's remarkably successful. It describes most metals extremely well. Also some insulators. You can add to this certain ideas on symmetry breaking. You can also add ideas on pairing, which we'll talk about soon, which leads to the BCS theory of superconductivity. And then put small corrections, and that basically is the entire theory. Okay, so I'm of course trying to oversimplify here a bit, but that's the basic idea of how the standard theory works. But then of course the purpose of the course, not right away, not today, but in a few lectures, is to talk about systems where this whole procedure fails completely. That you have you cannot think of the many particle wave function as just the product, anti-symmetrized product of single particle states. But while we are talking about this, let's just talk about another extension of this idea, not from the ground state, but to the excited states. So let's talk about excited states. So you had excited states, what would you do? So the ground state is just one state. So if you have, roughly speaking, if you think of each, if you have n degrees of freedom, if you have n degrees of freedom in a lattice, say, in a many-body system, the total number of states available to you, assuming that, okay, let's take a very simple estimate. Each point of a lattice can either be empty or occupied. Roughly, it's 2 to the n, something like that, 2 to the n states. So the entire spectrum of the Hamiltonian is incredibly huge. This is 2 to the 10 to the 23. That's how many states we're talking about, if you want to talk about the excited states. So it's hopeless to write down wave functions for that many states. But let's say you're only interested in the low energy states, those near the ground states. And often what happens, and this is an extension of the simple product picture I mentioned here, is that the low energy states can be written as combinations or sums, if you would, combinations of quasi-particles. And in fact, this assumption is also actually very, very powerful and general, and works even for many states for which the product assumption from the ground state doesn't work. But let's just talk about these types of states for now. Let me add another page. Okay. So what is this? What do I mean by quasi-particles? Well, it just means that if you have some state E, some excited state, this is some energy of some excited state. Well, to begin with, you can say, well, I put the electrons in some orbital in the ground state. So this is sort of very much like a chemistry picture. You have 1s, 2s, 3s, 3p, and you put electrons in every one of those orbitals. So in chemistry, how do you think about an excitation? Well, you say, okay, this electron gets excited from this orbital to that one, this one gets excited from this one to that one, and then you describe the many particle state, the excitation, as a combination of these different single orbital excitations. So each one of these single orbital excitation is what we'll call a quasi-particle, okay? So what we'll say is that there's some set of energies, which we call E alpha, which are single particle excitations, and we're going to sum over alpha. And then we'll put an n alpha here, telling us whether that particular orbital or state is occupied or not. So you'd say n alpha, oh, come on. N alpha equals, let's say these are fermions, 0 and 1. Okay, and we'll say we can think of at least the low energy state as simple occupations of of these single particle states, which we call quasi-particles. Now, this turns out not to be enough, as you'll see in a few minutes. You have to think about interactions between them. So imagine, you have a very big system, and here you have some orbital in which you excite a particle, and then there you have another one that you excite a particle. Well, if you excite enough of these over here, that will influence the energy of this one. So we say, well, okay, maybe these particles, once you excite them, if they're occupied, they're going to influence each other's energies. So epsilon alpha beta, epsilon alpha beta, there's some interaction between the particles, which I call F alpha beta and alpha and beta. So this, if you wish, is some labeling of the excited states in terms of single particle like excitations. Now, and you can add even higher order terms. So now we have all these free parameters that we haven't specified. What are these single particle energies? What are these interaction energies? This is basically what we want to determine when we are doing an actual theory, in, say, in 295B, what these numbers are. But one thing I want to emphasize here is that this kind of decomposition is very, very, has much fewer variables than you would think you needed, because you're talking about an exponentially large number of states. The total number of excited states, let's say, is of order 2 to the n. But the total number of parameters you have here, maybe there's another color. Maybe there's n of these epsilon alpha, n particular orbitals, and F alpha beta, being very rough, would be n squared. So it's really the number of parameters is polynomial in n, some polynomial number of parameters. Whereas the number of states is exponential in n. So we really, when you make the quasi-particle assumption, you're making an extremely strong assumption that the many particle states, very, very large number of states, can be written in terms of a much smaller number of parameters. So when you put it this way, you see this is really a remarkable assumption that it's amazing that's even correct. But in fact, it is correct at low enough temperatures in many, many systems. In some systems, these quasi-particles are very simple. They're just basically, like I said, in chemistry, just one electron hopping from one orbital to the other. But in other systems, as we'll see, these quasi-particles can be more complicated. They're not just one electron moving from one level to the other. They can even be fractions of an electron. You can fractionalize the electron in addition to taking combinations of little electron excitations. You can fractionalize it. And those fractional quasi-particles can also serve as a basis for many body states. And that's kind of where we want to go, is to understand how we describe these fractionalized states and the fractionalized quasi-particles. So let me just write that down here. Back to blue. So quasi-particles can be electrons. Whoops. I don't know what happened there. They can be electrons. They can be sometimes electron hole pairs. They can be electron-electron pairs. So these are, kind of easy to understand. You're just taking pairs of excitations and binding them in some way. What's more remarkable is that they can also be fractions of an electron. And that'll be the subject of much later discussion. Okay. All right, so that's the general idea of what is a quasi-particle and how it's a very powerful tool. For most of the course, it will be a very powerful tool for describing the excited states of a many-particle system. And, and it's remarkable, and we'll see why to some extent. It happens that you can use a polynomial number of parameters to describe an exponentially large number of states. That's the, the essential, that's where, why you need some theoretical analysis to be able to understand how to do that. If you just put it on a computer, it's impossible to really say something under control for this many states. All right. Okay, any questions? Okay, so now let's do something very definite. Let me just talk about, let's begin with free electrons. So free electrons, let's say they're moving in free space, they have some dispersion, h bar squared k squared over 2m. And we were going to work in the grand canonical ensemble, so there's some chemical potential mu. And therefore, I'm going to ignore spin for now. And C is the electron annihilation operator, is the creation operator. They're just free electrons. Okay, we can solve this problem very quickly, and let's just do it. So epsilon p now will be just this number here. Okay, so that's epsilon p. So what is the ground state? Well, here we're going to talk about ground state in the grand canonical ensemble. We just imagine that we have some freely available reservoir that can add and remove electrons. It's much easier to think about Fermi systems, especially in that language. So we can freely add and remove electrons, and then we can ask, well, what is the lowest energy state in this ensemble, for this Hamiltonian, the lowest energy many-body state? Well, what you really have to do is occupy all the states with negative EP. So anything that has a negative EP will be occupied, and anything that has positive EP, you leave it empty. So that's the ground state, is just the product of the fermion creation operator on the empty state with C dagger P. So this then introduces a boundary between the occupied states and the empty states, and that's what's called the Fermi surface. So if I draw the momentum P here, Px, Py, then there's a surface, in this case, just a circle, where epsilon P is 0. And in the ground state, everything in here is occupied, and everything outside is empty. And the boundary is the Fermi surface. Okay, so the boundary is it's a boundary in the discontinuity in the fermion occupation number. What did I do? Okay. All right, so what are the excited states? Well, this is also very simple. Now, again, thinking in the grand canonical picture, you can add a particle. But however, because of the exclusion principle, I can only add a particle outside the Fermi surface. Only here can I add a particle. So I have C dagger P acting on the ground state. That's an allowed state. It's an excitation. It has an excitation energy, EP greater than 0. By definition, the energy of any excited state must be greater than 0. Or I can remove a particle. Well, I have to remove it from the inside, then I can't remove it from the outside. So I take Cp, I make a hole, as it's called, with energy P inside the off. So now the original state G gained some energy EP, which is negative. Now you've lost that. So your new energy is changed by the excitation energy is minus EP, because you've lost the particle that was sitting in EP. And since EP is less than 0, this is also positive. Okay. So now if I go along this axis, along some axis from inside to outside the Fermi surface, just pick some radial direction, then what you see along the radial direction is this is your excitation energy of these are quasi-particles. These are particles, really. There's particle-like excitation with positive charge here. There's negative excitations. There's excitation with sorry, you're thinking of the electron as a positive charge. Sorry about that, but let's just imagine the electron is positive. So these are particles with positive charge. These are holes with a negative charge. And they both go to 0 right at the Fermi wave vector, PF. So there's some Fermi surface characterized by some Fermi momentum or Fermi wave vector related by a factor of h bar, where there are 0 energy excitations. Costs hardly any energy to create a particle or hole right near PF. So it's not surprising that when we talk about an electron gas, all of the action happens right near PF, because that's where the low energy excitations are. So this kind of system is called, has gapless. It has no gap to excitation energy. You can have excitations arbitrarily close to the ground state. And these have, they're particle-like above the Fermi surface and hole-like inside the Fermi surface. Okay, and the excitation energy is mod EP, which vanishes on the Fermi surface. Okay, so that's free electrons. So now, of course, nobody cares about free electron. Nothing is free. What happens when you add some interactions to this Hamiltonian? So we're going to add some other terms here and then ask what happens. And amazingly, it turns out that much of this picture survives. At least perturbatively, you can show to all orders and interactions. And in real life, in experiments, you also find it's true. And it survives in the following way. Basically, all that happens when you put interactions is that you just put a quasi in front of everything. These become quasi particles, and these become quasi holes. And their energy still vanishes. There's still a locus in momentum space where the energy goes to 0. So what do I mean by the quasi? Well, suppose you added an electron here. Suppose there was an electron sitting there. Let me draw a picture here. Here's my Fermi surface. I take a particle and I put it here. Now the particles start interacting. So what this particle can do, it can scatter off to, it can, let me take another color. It can scatter from here to there. You have to imagine that it's got to lose energy, otherwise nothing else will be allowed. And then some particle inside, you could take a hole here. It leaves behind a hole, and it gets scattered to a particle-like state over there. All right, so there are these processes that can happen right near the Fermi surface, where any particle that you create can create even lower energy particles. Now, this process has to conserve energy, so my picture is not very good. Let me try to make it a little better. So here's my original particle. Say it was here. I'm going to just exaggerate the whole thing. So this particle, it gets scattered. Let me also remove it from here. So I'm going to put the particle over here. And what this does is this particle gets scattered to some other position here. And then there's a hole that you create down here. And that gives you another particle that gets scattered to, say, over there. Now, what must happen when this process occurs? The energy must be conserved. So if you're thinking of kind of real scattering. So the sum of the energies of these 3 points, this point, and this point must add up to that. It doesn't quite in the picture, but imagine that it did. Okay. And this particle, of course, went from here to there. So what you can see, and this is really what makes this whole thing work, is that the phase space for this process becomes smaller and smaller and smaller the closer you get to the Fermi surface. As you approach the Fermi surface, it's not possible to scatter anything and conserve energy because of the exclusion principle. Okay, so these particles, turn out to live a long time. When you're talking about what I'm talking about here, real processes where you're actually scattering off and creating some asymptotic states. On the other hand, they can be virtual processes, the kind you describe in time-independent perturbation theory. Well, as this particle is moving around with some momentum p, it's creating a cloud around it. Okay, so here's my little particle. It's moving, and it repels some of the electrons near it, so it creates like a polarization cloud, or a vacuum polarization is sometimes called. It moves an electron. Again, I'm flipping the sign of the electron. It moves some electrons out from there to there, and there's a virtual cloud on it. So this whole thing, the particle with this cloud of particle-hole pairs, is what we call the quasi-particle. Okay, so what does this mean? This means that at the end of the day, there are still particles and holes. They're quasi because they have a cloud around them. But otherwise, other than the cloud, they live forever as you approach the Fermi surface. So that's why the quasi-particle picture works. All right. So now let's just see how this works out in an actual calculation. So but that's the basic idea. So that's the essence of Fermi liquid theory. That the excitations of an interacting metal have quasi-particles and quasi-holes. The energy of the excitations vanishes on the Fermi surface. So there's a thing called a Fermi surface where the energy goes to zero, where the holes turn into particles. And on the lifetime of these excitations, these excitations can decay. The lifetime goes to infinity as you approach the Fermi surface. So the whole picture becomes better and better the closer you are at the Fermi surface and the lower your temperature. All right, so let's do a calculation. Okay, so first we have to make a technical change to my simple description. It's actually really a nuisance in doing calculations to keep track of holes and particles separately, and then also have to constantly remember to take this absolute value, and then this is positive, the NH excitation energy have to be positive. The bookkeeping is horrendous if you really try to do it in this language. But there's a trick. It's just a mathematical trick. It's not something physical. It's just a trick, which allows you to keep track of which is a particle and which is a hole in a more simple way. So this is just a convenience, as I say, it's just a convenience. We postulate that the ground state is also made up of quasi-particles. I mean, quasi-particles really had to do with low energy excitations. But let's just postulate, we think of the ground state made up of quasi-particles with their number n of p given by this function. It's a step function. We call this the n0 of p. Okay, so this function goes like this, and it has a discontinuity at pf. Okay, 1, 0. We just postulate that the ground state. We think of the ground state as quasi-particles with this distribution. Now, of course, this is exactly true in the free electron picture, and it's not really true in the actual many electron picture. But this is just a bookkeeping trick to avoid all these absolute values. Okay. And then when we think of excitations, we'll think of excitations as changes in the quasi-particle number, delta n of p. So n of p is the number of, say, electrons at momentum p. And the number of quasi-particles will be delta n of p minus n0 of p. So delta n of p is it's really the actual number of quasi-particles near the Fermi surface. It's the physical quantity. Both n of p and n0 of p are kind of quantities that are not particularly well defined or useful, but it's the difference that gives you the quasi-particle excitation energy. So what we're interested in really are changes in the distribution functions. So the distribution function, for example, will change from this to something like this as you raise the temperature or something like that. And then what you see here is what you've really done in real life is that you have some delta n of p is negative. So in this region, delta n of p is negative. And what we're saying is that quasi-holes we'll think of as excitation with negative quasi-particle number. So these are holes that you've created here. And so that's where delta n of, and sorry, what happened there? Yeah, and then there are particles over here where delta n of p is positive. That should be less than 0. Okay. All right, so then we can write the energy of the quasi-particle. So this is now equivalent to this expression here. So here we were just adding up the quasi-particles in a very abstract way. This expression here, we were just adding up the energy of the quasi-particles. But now we think of the holes as having negative occupation number and having negative energies. And the two minus signs compensate for each other. So now our excitation energy is EP times delta n of p. Notice there's no absolute value. So what happens when you have a hole-like excitation, EP will be negative and delta n of p will also be negative. So the product will be positive, as it has to be because you're talking about an excitation. And conversely, when EP is positive, and you're talking about a particle-like excitation, delta n of p is positive. So there it is. So just a very simple bookkeeping device. Once you do the subtraction, and all absolute values have disappeared. It just makes life a lot simpler. And so now our quasi-particle excitation energy looks something like this. So here's P and EP. So, this is, of course, speaking very loosely, we have some energy that goes through zero. And we have negative energy excitation. Now, but just by definition, that's a ridiculous statement. And excitation always has positive energy. But this is just, as you see, it's just a bookkeeping device. These are negative energy, but the occupation number of these states will also be negative. When you create a hole like here, that means that has occupation number -1. You add a particle here, the occupation number is +1. And so the product is always positive. All right. And now comes so that's, so far, everything I've done could also be done for free electrons. And now comes, Landau's main insight, that to leading order, we have to keep track of, we can't just ignore the interaction between the quasi-particles. They live a long time. So one thing the interaction, before I get to that point, one thing the interactions will do is make this EP, it's going to be it's going to be some function, say it'll be something like p squared over 2m star. So it'll be some effective mass called m star of the quasi-particle. That comes from all these cloud of particle hole pairs around it. So that's one relatively obvious change that interaction must induce. They just make the electron a bit heavier, usually, than you would naively think. But there's also this interaction to worry about. Why should you worry about this? So here's the kind of reasoning that Landau gave. So delta N of, imagine at very low temperature. And if you go look at this, this is the Fermi distribution function at finite temperature. And you must know that this distance here, this over which delta N of P is non-zero, is of order temperature. So delta N of P is, of order temperature when you integrate over it. It gives you a factor of temperature. And EP itself, which is the value of the excitation energy, is also of order temperature. So just by naive counting, you would say that this term is not of order temperature, it's of order temperature squared. And in fact, if you just compute the energy of a free electron gas at finite temperature, you'll find that the correction to the energy goes at temperature squared. So that's a problem in StatMech. Maybe you've done it before, or maybe it'll be in the homework, so on. But by the same reasoning, how about this term? Delta N of P is of order temperature. This is of order temperature, but this is also of order temperature squared. So we do have to worry about the fact that even though the density of quasi-particles is very small at low temperatures, the kinetic energy change is also of order T squared. So we also have to worry about interaction corrections of order T squared. And these coefficients are called the Landau parameters. Okay. So both terms of order T squared are of order P minus PF squared if you're working at zero temperature. And that's it. We don't need anything else. So this for a metal at low temperatures with a Fermi surface, this is the complete theory for the low energy quasi-particles. It's characterized by one effective mass and then these Landau parameters, which are two functions of P prime. Now, typically you have a lot of symmetries in the problems, cubic symmetry on a cubic lattice, and this strongly constrains the form of this FPP prime. Furthermore, we only need this FPP prime right on the Fermi surface. We're always assuming that everything, all the action is happening in this little region. All the scattering at low enough temperatures will be happening way down here.
Sorry, does mu get re-normalized by the interactions at all, or
no? Yes, it does. I mean, it depends what you mean by mu. So that's another interesting point. So if you mean by mu, precisely mu is a thermodynamic quantity. It's well, at zero temperature is dE dN at T equals 0, and this certainly gets renormalized. Okay, so mu gets renormalized, and so naively you would say, well, if mu is renormalized, the value of PF. So remember what mu determined in this theory was where this energy went to zero. If mu is changed, the point at the momentum at which, sorry, that should be P. Apologies. P. The momentum at which this goes to zero is going to change. Okay, so initially you would think that means that the value of PF is also going to change because of changes in mu. There could also be changes in the dispersion. This is if you had a lattice. This could be some very complicated changes in the dispersion. There can be even corrections to various quantities here. This is not really mu that appears here. This is mu, which is the physical mu. The mu that appears here is some other number for an interacting system. So they're the same for non-interacting system. However, and this was actually one of the points I wanted to get to today, but I don't think I will. There is a very deep theorem called the Ludinger theorem, which says that the volume of the Fermi surface is independent of strength of interaction. So this volume, the volume of occupied states, is independent of interactions. Okay. I won't really prove this now. Maybe later in the course, there's a proof in all the textbooks involving many pages of Green's functions, which is summarized in these notes if you want to look at it. But today there's much nicer proofs based on a more topological argument that maybe later in the course we can talk about, or one of you can make that your presentation topic. Any other questions? Yeah. Okay, this is really the way you normally write it. Since you're only interested in EP near the Fermi wave vector and EP vanishes, so just do a linear expansion. And then there's only one quantity that you care about, which is the Fermi velocity. And for a free electron, that'd be PF over M. But for interacting electrons, it's over some M star. So yeah, so I should have been a little more careful here. Calling this is mu, this is strictly, that's an important, this is strictly speaking equal to mu only for non-interacting electrons. For interacting electrons in any system, this is the more general definition of mu, and that certainly does change. But the position of the Fermi surface, the shape of the Fermi surface can change, but the area or volume enclosed by it does not depend on interactions. And for an interacting system, of course, we define the Fermi surface as the location of zero energy excitations in momentum space. So in this grand canon, normally we always assume that if you have some particle, is dispersion going to be minimum at p equals 0? That's the starting assumption in any course on quantum field theory. But it's not true in a metal. This is a particle whose excitation energy is not at p equals 0. It's on a sphere or a circle if you're in 2 dimensions. So it's a very strange looking dispersion, which goes through 0 on this surface. Here's one section of it. Yeah. Sorry, here. Okay, any other questions? All right, so then there's a calculation here of the specific heat and the compressibility. Let me just very quickly go through it. You can read it later. I mean, we're not going to really use much of this later. Just want you to get the general idea. So suppose you heat up the system. Now, if you had free electrons, I presume you've done the calculation in your StatMech course. The specific heat is linear in temperature. Roughly speaking, that comes from the fact that the excitations electrons are excited over a width of order temperature, and the typical energies are also of order temperature. So if we integrate over all the excitations, the energies of order t squared, like I said earlier. So if the excitations of order t squared, the specific heat, which is dE dt, is linear in temperature. So that's a very fundamental property of a Fermi liquid, that the specific heat is linear in temperature. But now we ask the questions, what about the Landau interactions? Are they going to change the specific heat? Amazingly, they don't. And why is that? Well, to figure out the change in energy, you have to integrate over in thermal equilibrium P and P prime. And what you notice about delta N of P when you look at this, that this is kind of, you take the integral under this region and this region, they're equal to order T cubed. So if the dispersion is linear, this thing, this area is equal to this area. So when you integrate over delta over P here, the sum over P, delta N of P goes to 0 with temperature. And therefore, this term doesn't contribute. So this is one of those bizarre things. There are interactions between the quasi-particles, but because of cancellation between particles and holes, doesn't change the specific heat. The specific heat is just the free electron value. All you have to do is replace M by M star, and you're done. Okay, so this is the well-known value of the specific heat. And excuse me, there should be a factor of temperature here. It's missing, where N of 0 is sometimes called the density of states in the Fermi level. On the other hand, for the compressibility, so what happens when you change the chemical potential a little bit, just a tiny amount? That's a little different. So again, you do the calculation for free electrons, where you change delta mu a little bit, and this is easy to figure out. So delta N of P will be just d by d mu of the change in C dagger P Cp. Now this C dagger P Cp for this Hamiltonian is just the Fermi function. So you have to take the derivative with respect to mu, and that gives you minus df dp. So one very useful thing to know, that if you take the Fermi function and take its derivative at at low temperatures, it becomes a delta function. So this is the statement that d by dE of 1 over e to the e over t plus 1, that's the Fermi function. This is equal to, as t goes to 0, minus delta of E. I mean, you can see that here. As t goes to 0, it becomes a step function, and the derivative of the step function is a delta function at this point. It's negative because the step function goes down. But you can formally just play with this and verify this. An important identity that's useful to know. Okay, so, oops. Where was I? Right, so that's minus df dep. Well, that's just a delta function, so delta of EP. So now you sum over P, you want the change in density due to change in chemical potential, then that's easy to integrate the delta function, and all you get is the density of states at the Fermi level. So the inverse compressibility, or dN d mu, of a free Fermi gas is the density of states at the Fermi level. Okay, so these are all, densities of states, Fermi function. These are all concepts I presume you've seen in your StatMech course, but if not, I'm sure you will be happy to discuss them further, and there probably will be just some review of these concepts in the first homework. Okay, but what about when you have the Landau interactions? Well, you do the same kind of calculation. So what happens when you have Landau interactions, the energy of any quasi-particle EP depends on the occupation number of all the other quasi-particles. So now you imagine the quasi-particles have this energy, where the energy of quasi-particles momentum P depends on quasi-particles with all other momentum P prime. Okay, so now you just, the change in density will be just the change in this energy times the Fermi function, and then you take a derivative, you expand this in small mu, and then just do some algebra. Okay, I'll just leave that. And the final result, the simple algebra is spelled out here, is this result here. It gets renormalized. So this is the so-called Landau renormalization. Because of the Landau parameter, the compressibility is corrected by this factor of 1 plus F naught. Okay, I'm sorry I went through that quickly. Mainly because we're not really going to need any of this in the rest of the course, just to highlight the basic properties of a Fermi liquid, and how, and how everything is parameterized, thermodynamic and many other quantities, in terms of the dispersion near the Fermi surface and these Landau interaction parameters. Okay, I think I'm out of time. So I have a little more to say where I actually do go through an explicit calculation of the lifetime of the quasi-particles and the statement of the Ludinger theorem. Yeah, I think I don't want to skip that. That's in fact the more important part, but we'll talk about that on Friday. Friday. Any questions? So everything I've written here is on the website, and the things that I have been writing, the scribbles, I'm sorry, well, some of them are not. I'll try to be neater. I'm also going to post this on the website. Questions? I mean, I admit that was fast. I mean, that's something that's covered over several lectures in 295B, but I just want to give you a flavor of it. We're not going to really need much of that since in the remainder of the course, but it gives you an idea how people thought about the effect of interactions, which could even be strong in the old days, where we just think in terms of extrapolating adiabatically from the free particle picture and just renormalizing a few things. So we still think of the many-body system as just made up of renormalized quasi-particles rather than the bare particles. But apart from that renormalization, it's still almost a free particle theory. So that's kind of the, the thing that we don't want to be when we talk about more exotic phases. But it's good to know the enemy, and so now you've met the enemy. Any other questions?
So I have a question maybe. So there are like, oh yeah, okay. So there are like several levels of approximation mentioned, right? So one of them was that we restrict ourselves to this like one term with interactions, for example, and then another one was this assumption that we made that all the like for the ground state, all the like the number of particles is like all particles, right? As far as I remember. So I was wondering, like, when the liquid like Fermi liquid theory breaks, is it always like drastic that the whole thing just doesn't work, or is there like sometimes, for example, including more terms or something like that might still make it reliable?
Well, some things do survive, as we'll see. The concept of a Fermi surface is much more general than a Fermi liquid. Its Fermi surfaces are present even in systems that have not Fermi liquids and have no quasi-particles. But it's still too early to talk about that. That's really towards the end of the course. But so let me not talk about breakdown. But Fermi liquid theory itself, it's really an exact theory. There is no other assumption other than continuity from the free particle state. So assuming you have some many electron system, which you start from free electrons and you turn up the interaction, and as you turn up the interactions, you can make the interaction very, very large, you end up with a Fermi liquid state. And the claim is that to leading order in temperature over the Fermi energy, which is, say 2 order T squared and in T over EF, all you need to know are M star and F. Now, once you know these quantities, all of these statements and results are exact. There's no approximation. This is really the leading low temperature behavior is fully characterized by the Landau parameters and the effective mass of the quasi-particles. Occasionally, you need to know more when you talk about more higher temperature dependent corrections. But if you're talking about long time, low energy, low momentum responses of a Fermi liquid, of a metal, you come in with some long wavelength response, you perturb it with light or whatever. As long as you're talking about low enough energies, this is all exact, no matter how strong the interactions. Okay. Now we can't prove, if you give me some Hamiltonian of some electrons, I can't prove it'll be a Fermi liquid. I can do an experiment to see if it is. And then from the experiments, I can say, aha, it looks like a Fermi liquid. So I should be able to fit everything, all the different experiments with these few parameters. And when you do that, it works. So there are many, many instances how that works very, very beautifully. So yeah, so it's not really an approximity, it's an exact theory. Built on the assumption of adiabatic continuity from free particles.
Thank you.
Yeah.
So there's this cloud that you were drawing of
Cloud?
for
Oh yeah.
a quasi-particle. How is this
Yes.
different from like a polaron? Or like, is this the same thing as a polaron, or how do they differ?
Yeah, you could think of it as a polar. I mean, this is mainly a question of terminology. So, you know, a polaron would be you have an electron. Typically, where is the cloud? Here's my cloud. You have electron, just one electron, say, moving through a lattice. Okay, so as the electron moves through a lattice, the lattice distorts around it. So it has a cloud of atoms moving. So polaron typically refers to an electron dragging some atoms around it, distorting the lattice around it. And that whole object is a normalized electron, sometimes called a polaron. Here, I'm taking a free electron gas in free, interacting electron gas in free space. There's no potential, there's no lattice, to simplicity. The electron is moving around, so it's going to repel the other electrons. Okay, so the electron, so if I, you know, let me plot, let me do this here, not there. Yeah, so say this is some location, this is R, and I put an electron here. So this is the electron density, rho of R. So I put an electron here at this point as R equals 0, so there's a delta function in the electron density. Now, when I'm very far away, the density will be some mean value, some rho 0. Okay. And what the electron effectively has done, it's going to, all the electrons that are near it, it's going to repel them. So it's going to have, if I measure the electron density, it'll be something like this. I don't know. It'll be depressed near the electron and then higher above the. So what I've done is I've taken some particle from here. This is now in real space, moved it to there. And I've taken some particles here and moved it to there. So another way of saying it, here's the electrons, and here are the holes. So you leave behind a hole. So so this is an electron hole pair. Is an electron, there's a hole in the mean density. The mean density if the electron wasn't there would be some line like this. So now what you do is you take some electron and move them from here to there, so you leave behind a hole. And then this is an electron hole pair, and here's an electron hole pair. And that whole thing together, all of this together, will move, and that's your quasi-particle. So it's an electron plus some electron hole pairs. And that whole thing is your quasi-particle. It has an effective mass, but once you set it, as long as the momentum of this composite object is near the Fermi surface, and you set this thing moving, it'll remain like a coherent whole for a very long time. It won't find anything else to scatter off of. Okay, so we call this a quasi-particle. You want to call this a polaron? Sure, there's terminology. Generally, the word polaron is used for not simple electron hole excitation, but other excitations. I mean, if you have a lattice, that will also distort. Everything else around the electron will distort a little bit, but the whole object will move with some renormalized mass, but should have a long lifetime.
Thanks so much.
I have a question.
Sure.
So we discussed this theory in the grand canonical ensemble, right?
Yes. Yeah.
And you argued why the Landau term, like the F term, needs to be kept.
Yeah.
So I'm wondering, in some experimental situations, I think there might be closed systems where you can't have a grand canonical. ensemble, right? Like cold
Yeah.
atom stuff. So like
Yeah.
in that case, is it possible to like describe this entire thing in like canonical ensemble, for example?
It is, but it's okay. First, let me make a point that just recall an important statement in StatMech. What we proved in StatMech was that in the limit as the system size goes to infinity, as n goes to infinity, the results of the canonical and grand canonical ensemble are the same. Okay, so unless you're interested in a very small system, so we're talking about a big enough system of size 10 to the 23, where n is 10 to the 23, then the fact that you have an experiment where the total number of electrons, there isn't actually any reservoir, is of no relevance, because all the quantities that you're measuring will be the same in both ensembles. So the choice of ensemble is not really directly related for a large enough system to the experiment situation. It's just a theoretical tool. It's much more convenient to think about the electrons having zero energy on the Fermi surface. Now, you can formulate everything you can formulate a theory if you wish, where the electrons have energy equal to EF on the Fermi surface. You can do that if you want. It'll be just much, much more cumbersome, but the results will be all the same. It's only when you're really concerned about the discreteness and the momentum and the fact that you have a finite system, a quantum dot, which is small, and then you do have to worry about the difference between. But for the most part in this course, we won't worry about small systems. We're talking about infinite systems where there's no difference.
Thanks.
Sure. All right, I think almost up to 4:15. That's fine with me. If it's fine with you, I'm happy to lecture for an hour and continue discussion as long as you want. Okay, but today I lectured less than an hour. They were all that introductory stuff. So, all right, great. So please do join the Slack and questions and comments. Let's see if we can have a community on Slack where we can all talk to each other. And I'm happy, of course, to have discussions on Zoom too. And tomorrow there'll be a section where how you can answer more questions on this lecture, and also he's planning to discuss review path integrals, starting from quantum mechanics and going out to field theory. Okay, so see you on Friday then, or on Slack. Bye.
Thank you.
Thank you.
Thank you.
Thanks.